Imagine that you're a scientist, which, if you're watching this video, you probably already are, and you learn that the latest shipment of wheat to the world's most famous cookie factory is potentially contaminated with a deadly mold-produced toxin. Being the problem solver you are, you're able to use a method called mass spectrometry to analyze the sample of wheat and detect the presence of the toxins. Mass spectrometry is a technique that uses a machine called a spectrometer to turn your sample into charged ions and measure the ratio of their molecular weight to their charge. This data is presented as a spectrum, with mass to charge ratio, m/z, on the x-axis and abundance on the y-axis. Since most of the ions that pass through the spectrometer are made to have a single +1 charge, the m/z value simply becomes reflective of the ion's mass. How does it work? Here's a simplified example of a mass spectrometer. The sample is loaded in, where it is turned into vapor through heat. This process is then separated into four main parts, the first being ionization. The vaporized sample is then bombarded by a beam of electrons, which allow it to become an ion, hence the name ionization. Let's zoom in on this process. Here's an atom in your sample. When these high-energy electrons come in, they have the power to knock an electron out of the atom's orbital. This then creates a molecular ion, which is a radical cation, a positively charged ion that now has an unpaired, lonely, sad electron. The next step is acceleration, where a magnetic field moves all the ions at the very same fast speed through the machine. The ions then enter the third step, deflection. This step is where the ions are separated by their mass. A magnetic field within this bend pushes the ions through, essentially like a gust of wind blowing the ions as they move around the curve. Smaller ions will experience more deflection by this magnetic field, while bigger ions will be less deflected. This brings us to our final step, detection. The smaller ions, which experienced more deflection, reach what we call a detector faster. The heavier ions that had less deflection arrive fashionably late to the detector party. As each individual separated ion reaches the detector plate, the data on their m/z values is sent to a computer software, which it can then generate our spectra. We can now analyze which ions are within our sample. Going back to our wheat example, we could compare the known molecular weight of our toxin of interrogation to our mass spectrum. However, in our creation of the unstable molecular ion, there's a chance of fragmentation, where our ion breaks apart into pieces. Knowing where your ion of interest could fragment and the molecular weights of those fragments is important for analysis. Thus, if we find a peak that corresponds with its molecular weight or its fragments, that would be a clear indicator that our wheat is unfortunately contaminated. While there is a sad recall of our well-loved cookies, the power of mass spectrometry was able to save many cookie lovers' lives, as well as solve many other real-life problems.